Hi again, Pre-Calc gang. Lesson 4.4 is what's on tap today, modeling and optimization. So you can see, and as you know, optimize means to maximize or minimize something. So that fits right into what we've been talking about in this chapter. So graphically, as you can see, this would imply we're trying to find a maximum point or a minimum point, either on a graph or some sort of equation. And of course, as you might also expect then, that would mean derivatives. That's why this whole lesson is in this particular chapter. So we'll be looking at a variety of real-life problems. We're going to split you up and give you and a partner a particular problem that you'll be solving and presenting. Again, lots of different types of problems here in science and business and industry and all sorts of things like that where we will try to be optimizing something. Now our general rules then, or our process in solving these kind of problems is, number one, we'd like to write some kind of equation for this thing we're trying to optimize. Maybe we're trying to minimize the surface area of a can that has a certain volume. Or maybe we're trying to maximize a profit. Or maybe we're trying to minimize an amount of fencing around a field or something like that. Any number of items like that are fair game for these types of problems. Second thing we want to do then is find the derivative and set it equal to 0. Again, that's been a common theme this whole chapter, and once again in these types of problems. And of course the reason why is because whenever we set that derivative equal to 0, that will tell us a maximum or minimum point, which leads us into the optimizing that we're trying to do in this lesson. So then we're going to try to solve that derivative analytically or graphically. Some of the ones we get, it won't be real nice to solve analytically or algebraically. We'll just have to try to solve it with a graph. We have to interpret our solution, because maybe the answer that we get isn't just the final answer, but that may lead to helping us find that answer and then solve the problem. So probably the toughest thing actually is maybe number one, just trying to write that correct equation, trying to get that all sorted out, because we know the derivative rules and how to do things like that. Alright, so we're just going to go through a couple examples here just to give you a taste for what these types of optimization problems are all about. And of course we'll see several different ones once we get into class. Alright, here's our first one. Find two numbers whose sum is 20 and whose product is as large as possible. Now, one thing I mentioned back there, I think, is when we write our equation, it would be nice to just have one variable, basically, in the equation. When we have two numbers whose sum is 20, of course, we could say this, x plus y equals 20, but we want to generally stay with just one variable in our particular equation here. So, can we think of a way that you can write a sum of two numbers that equal 20? Well, perhaps it might look something like this. If one of them is x, then the other one we could think of as 20 minus x. And obviously if you add these two things together, these two expressions together, the x's will cancel out and I'll get just plain 20. Now we want the product to be as large as possible. So here's the equation we want to really write, something about the product. So the product of these two numbers, one of the numbers would be, and I'm just going to use p here for the product. We're not really going to use that as a variable, but just to designate that. The product would then be x times 20 minus x. Those are the two numbers. They multiply together, they add together to be 20. Multiplying them together, we're trying to maximize that. Well, if I go ahead and distribute, I'm going to get 20x minus x squared. And we would see that if we went ahead and actually drew the graph of that, that it would be an upside down parabola. So we're really, of course, trying to find that maximum point up there. What gives us the maximum? Well, once again, let's think about what this whole chapter has been about. To find maximums, we of course find the derivative. So I'm just going to call it p prime in this case. And I follow my derivative rules, which would just give me 20 minus 2x. So there's my derivative, and once again, as a common theme that we have been undertaking this whole chapter, I want to set that derivative equal to 0. So I do that. I'm going to get my 2x on the other side, so 20 equals 2x, and sure enough I'm going to get that x equals 10. If you did this on your graph, if you graphed your original function, which would be this one right here, producing this graph, sure enough, what do you think would be up at this highest point? Yeah, that would be when x equals 10. Okay? Obviously, the other number would have to be 10 as well, and that tells you where the maximum product would be. 10 times 10 would give you your maximum product. All right, so that is our first example there of optimization. Let's tackle a little bit more perhaps. All right, so we have a rectangular strawberry patch, and it's got to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence, and how much fence will be needed? Alright, so first thing I'd like to do is try to draw a diagram, I think, of this. Always a good plan. So it's rectangular, like this, but it has to be split into 2 parts. So we're going to have fence all the way around here. Now, if I call this width here x, notice I really have 3 of those x's. Now, the tricky part is what will I call the length? Well, I do know that it is 216 square meters in area. So that means length times width would have to be 216. So here's a tricky thing. See if this makes sense to you. I'm going to call this length 216 divided by x. Because do you see that if I multiply the length times the width here, what happens? The x's cancel out and I get 216, which matches up that area there. Now, that's my diagram. Now when I write my equation here, what I'm going to do is try to write it, remember, for the thing I'm trying to optimize. So in this case, notice I am trying to find the smallest amount of fence. The smallest amount of fence. So I'm really looking for the perimeter. Can I write an equation here for the perimeter, and really not just the perimeter, but for all the fence that I need? So certainly I need 3 of these x's because, yeah, there's going to be a fencing here, here, and here, so there's 3x. And then I also need 2 of these lengths here. So that's 2 times 216 over x. That's a little strange, but that's an expression for the length of the fence that I'll need. Now notice if I kind of multiply this out a little bit, I'm going to get 3x plus 2 times 216 is 432, and I could write that as 432 over x, but I'm going to write it as x to the negative 1. And you probably have an inkling why I would do that, because of course now my next step is to find that derivative. So my derivative here, of the derivative of 3x is just 3, and of this other thing it's going to be negative 1 times 432, and then x to the negative 2 power, like that. Now that might look a little strange. How am I going to try to solve that? Remember, I want to eventually set this equal to 0. Well, I'm going to do a little dipsy-do here. I'm going to actually write this back as a fraction. So do you see that this turns into the fraction 432 over x squared? And again, I want to set that equal to 0. Which is kind of strange, but that's the way it looks. Now I'm going to go on to another slide so I have a little bit more room here to keep working. So now I'm going to rewrite that a little bit. I'm going to get that 3 over to the other side. So I have, maybe I'll get the 432 over to the other side so it's positive or whatever. In any case, I'm going to have 432 over x squared equals 3. Now you might notice that, and again this is, I've already set this equal to 0, I really have a little proportion here, don't I? And you might remember from your middle school days how you can solve proportions. Do a little cross multiplying like this. So in this case I think you see I can get that 3x squared will equal 432. I can divide both sides by 3. So I get x squared equals 144, kind of a nice number. And sure enough, then x is going to be plus or minus 12. Now obviously in this case we don't want the negative 12, doesn't make sense because in this case we're talking about the amount of fencing that's needed, so the negative doesn't make sense. That is something we'll have to consider when we solve these, is make sure when you get your final answer that you put it back in the scenario of the problem to make sure it makes sense. Alright, so the dimensions then of my strawberry patch, my x is going to be 12, so it's going to be a width of 12, and remember it was 216 divided by 12 for the length, and that's going to end up to be 18. So there's my dimensions, 12 by 18, and the total fence, the total length of fence that I need, remember we have that stuff in the middle there, so I'm going to need 3 times 12, because there has to be one here, here, and here, right? 3 times 12, and then plus 2 times 18. So the total amount of fence I need is going to be 72 meters. That's the minimum amount of fence that we need. Remember, if I actually graph this derivative here, it would be a parabola that would be opening upwards, so it would have a particular minimum in this case. Alright, so thanks for listening, everybody. Now you have at least a little taste of optimization problems, which we'll be working on in class. So we'll see you then.